Perfect. Should be recording. Okay, so rates of reactions, catalysts, reversible reactions. So in terms of easiness, hardness, if that's even a word, I'd probably say rates of reactions is pretty easy. Catalysts is also, I guess, easy. Reversible reactions is probably where it gets a bit harder. We also have bond energies, things like that, but I won't be going through that today. We did do a previous crash course on endothermic and exothermic reactions that is available for purchase. So let's start with rates of reactions. Before I start to teach, I'm going to ask, like, if anybody can, can somebody tell me what the word rate means, or give me a definition of what the word rate means in rate of reactions. So someone said quantity of product produced per unit time, speed, the time taken for a chemical reaction to occur, how fast reactants are converted into products, how frequent, how fast something happens. Yeah, you're all on the right line. So it's basically the rate of a chemical reaction. So the rate of a chemical reaction is how fast the reactants are changed into products. So again, depending on your example, I probably wouldn't say how quickly a reaction happens. I'd say it's the time or how fast the reactants are changed into products. So I'm just going to write that here. So how fast reactants are changed into products. And before I go on, can someone give me the definition of a reactant and a product, just so everybody is aware? Does anybody know what a reactant is? Put it in the chat. Or what a product is. Yeah, good. So if we have X, chemical X plus chemical Y, and that goes to, let's just say, H2O, which is water, plus another, let's just say, plus A. These here are the reactants because they're reacting together. And what's being formed, which is this, they are the products. Okay. So let's have a look at this graph quickly. We need to understand graphs because graphs are horrible and we need to understand them. So here we have a graph that shows the rate of reaction of calcium carbonate, but in different forms. By different forms, I mean whether it's large chunks, small chunks, powdered, or twice the mass of powdered calcium carbonate. So what can we see here? What can we see? What color line shows the slowest rate of reaction? What reaction is the slowest? Purple. Ava said blue. Someone said blue. One person says blue. Now, the reason why it isn't blue is because if we look here, it says volume of gas. So if more volume of gas is produced in a shorter time, that means that the rate of reaction is faster. It is purple, again, because we can see by the gradient, it's less steep. Purple levels off at the slowest rate, good. And why is it the slowest though? Does anybody know why it's the slowest? Good, it has a large surface area. It's not a small surface area. Because larger surface, okay, is it larger surface area or smaller surface area? Tell me. Like some of you are saying larger, some of you are saying smaller. Tell me what it is. Larger, and can you explain? Explain. Smaller surface area, small chunks. Large for blue, so large surface area for blue, okay, fine. Because less areas are exposed. Small surface area. Okay, so basically, if we want a faster reaction, like a really, really fast reaction, we need a large surface area. Whereas if we want a slow reaction, like this purple one, which are large chunks, if they're large chunks of calcium carbonate, it won't react fast because the surface area is too small for the reactants to work on. Okay, so why might large chunks have a slower reaction time? How would we answer this in an exam? Why might the large chunks have a slower reaction time? Does anybody know? Good, it has a smaller surface area to volume ratio. So basically that means that the particles are less, so less particles are exposed to the surface, like Emma said, and it reduces the frequency of successful collisions. I'll come on to collisions and collision theory in a second. Now, what about this flat line? What do you think this flat line represents? What do you think the flat line shows? Yeah, exactly. It shows that the reaction is finished. Great. And what must happen for particles to react? Does anybody know what must happen for particles to react? Collide. Yeah, good. So they need to collide with enough energy or enough activation energy. Activation energy. Can anybody define activation energy? Because this is a key thing you need to know. The amount of energy needed to start the reaction. I wouldn't say that, no. I wouldn't say just the amount. Yeah, so like someone said, it is the minimum energy required to start a reaction. Good, and what we will learn about catalysts is that they lower the activation energy. So if they lower the activation energy, we have a faster rate of reaction. Okay, so does everybody understand what I've done so far? What's a catalyst? I'll come on to catalysts in a second. They basically speed up the rate of reaction. Yeah, okay, I'm assuming everybody has understood. Let's quickly talk about collision theory. So collision theory, this is pretty important. Can somebody tell me in a couple of keywords what collision theory is? Good, yeah. So basically, the more collisions there are, the faster the rate of reaction. So the more collisions equals faster rate of reaction. Good. So for example, if you increase the temperature, that means more collisions. Chartier's principle, yes, exactly. Some examples don't need to know that, but okay. Now, what happens during a collision? What is a collision and what is a successful collision? So a collision is basically where energy is transferred from one particle to another. And in order to become a successful collision, they need to sort of collide with as much energy or like enough energy so that it can be successful. Okay, so basically imagine lots of particles here. They're just colliding against each other. Do you guys know about enzymes? Do you know about enzymes? So it's like the lock and key model, but that's for biology. But this is sort of for, you don't need to know in detail, but it's sort of like on the same principle. That's a biological catalyst, like as I said. Great. Okay, let's quickly talk about activation energy. So as I said, activation energy is the minimum amount of energy that particles need to react. And why do they need this energy? Minimum amount of energy Why do they need this energy? Create successful collisions. Okay. I wasn't thinking about that. No. Do you guys know about bond breaking, bond making? It's because they need enough energy to break the bonds. And the particles need enough energy to break the bonds. Good. So the bonds in the reactants need to be broken so that they can start the reaction. And how can you supply this energy? How can you supply this energy? One answer I'm looking for. Yeah, I'd say heating it up. Good. So that's collision theory, pretty simplified. Does everybody understand collision theory? So the more collisions, the faster the rate of reaction. Question, yes, Anna, what's your question? In the collision theory, does the speed of the particles also affect the theory? Yes, it does, and I will come on to that in a second. So in terms of speed, the faster the particles move, that basically means they have more kinetic energy. If they have more energy, they collide with greater force or greater energy, and that causes a successful collision. But there are other ways you can increase the rate of reaction that will come on to in a second. So let's talk about temperature. How can temperature increase the rate of reaction? Does anybody know? Does anybody know how temperature can increase the rate of reaction? Yeah, so the particles gain more kinetic energy. Now, kinetic energy is basically energy. It's basically the speed at which the particles move, as like a simplified explanation. If the particles are more like moving very, very quickly, they have a lot of kinetic energy. If they're not moving very quickly, they have less kinetic energy. So if you increase the temperature, increase temp, that means particles gain more kinetic energy. Obviously, if you decrease the temperature, they lose kinetic energy. Now, if they gain more kinetic energy or more speed, they collide faster. So more successful collisions. At a faster rate, and therefore greater rate of reaction. Does everybody understand that so far? I have a question. Yeah, ask questions. Okay, so let's move on to concentration and pressure. Does anybody know what concentration is? Is it used for bond making? I'll come on to that. Off-topic question. I'll leave off-topic ones to the end. The amount of substance, that's not enough. Amount of solution, that's not enough, because amount, it doesn't really give me anything. Because amount, I could just say, oh, I've got a lot of deodorant in my room. The number of particles in one volume, yes. So the concentration is the number of particles in like a given volume. So if a solution is made more concentrated, it means that there are more particles of the reactant like closer together, and that means they are more likely to collide. So more concentrated means that more particles in like a unit in that more particles are crowded next to each other. And then what does that mean? What does that mean? If more particles are crowded together, does anybody know what that means? More collisions? Yes. So more concentration, more particles in a given area. Therefore, more successful collisions. Good. I feel like I'm spelling this all wrong. Have I like collisions? How do you spell collisions? C-O-L-L-I-S. Collisions. More successful collisions. Good. What does that mean? If they have more successful collisions, what does that mean? Good. It means greater the rate of reaction. Can you teach more slowly? I can't. That's the problem. I wish I could, because I have to go at like literally at 7:30, so I need to get all of these topics done. But the recording will be available as well as these notes. What else can you add to this? What else can you add to the concentration or pressure? So if you increase the concentration or pressure, good, collide more frequently. So I would put that here. They collide, particles collide more frequently. So faster rate of reaction, yeah, a greater rate of reaction or a faster rate of reaction. Good. Now, what's the difference between pressure and concentration? Does anybody know what concentration is? Does anybody know what pressure is? Let's move on to pressure. Pressure is for gases. Good. Pressure is for gases and concentration is for liquids. Good. So what about in a gas? If we have, let's say in a balloon, if you increase the pressure in a balloon, the particles become more crowded. They become like sort of compact. And if they become more crowded, the frequency of collisions will increase again, and therefore the rate of reaction will increase. Good. Great. So does everybody understand that so far in terms of temperature and concentration? Here, I'd just add collide more frequently. Yes, 100%. Great. Okay. Let's move on to surface area. Surface area is a little bit more tricky, not too much. It's not too hard. So let's talk about surface area. I'm just going to draw two objects. We have one here and we have one here. Which one do you think has a higher surface area? So let me quickly, and then which one do you think has our higher surface area? The smaller ones, yeah, the smaller ones have a higher surface area, but why? Why do the smaller ones have a higher surface area? Yeah, good. The more particles, so it's exposed more, basically. It's exposed more. So more space for the particles to collide, exactly. So if you break up a larger object or a larger substance into smaller pieces, it will increase the surface area to volume ratio. So more of the solid will be exposed compared to the actual volume. So let's say I have like I have this cuboid in my room of perfume. If I just dunk this in acid, it will react really slowly. But if I cut it up into small pieces, it will react much more faster, just because more of it is exposed to the acid. So if you increase the surface area to volume ratio, I'm just doing it like this, surface area to volume ratio, by breaking it up, breaking substance up into smaller pieces, the rate of reaction increases. Now you have to ask yourself why. Keep asking yourself why. Why? Why might this happen? Good. They have more space for the particles to collide. So the particles will have more area to work on, and therefore the frequency of collisions increases. So does everybody understand this so far? And therefore the rate of reaction is increased. Great, okay. So let's move on to catalysts. I'm pretty sure everybody here knows what an enzyme is, but an enzyme is a biological catalyst. So a catalyst is a substance that speeds up the rate of reaction. I'm just going to write it like that. But how? How does it do this? By providing an alternate pathway, pathway by lowering the activation energy. One key thing you need to write is they don't get used up. So in terms of a past paper would usually ask alternate part. So a past paper usually ask, how can you tell that a catalyst was used? It's because the mass doesn't change, because if the mass had changed, it wouldn't be a catalyst, because remember, the mass of a catalyst will always stay the same because it can't be used up in a reaction. Okay, so using a catalyst will increase the rate of reaction because the particles, so remember how I talked about lower an activation energy? If the particles need a lower activation energy, they need less energy to get a successful collision. And what does that mean? Can somebody tell me what happens? Does anybody know what happens? The rate increases, yeah. Yeah, so basically more particles have at least the minimum amount of energy needed for a reaction to occur when the particles collide. Okay, great. Question, yeah. Okay, so let's look at a bit about exothermic and endothermic reactions. I won't go into them in too detail just because that was covered in a previous crash course. Let's look at an exothermic reaction. Can somebody sort of describe this? Can someone describe this diagram? Can someone describe this, this here? What is this and what is this? What is this triangle and H? Does anybody know what this sign means? Or it's a Greek letter. Yeah, it's the delta. It's delta and H. It's the enthalpy change. Good. It's the enthalpy change. And then does anybody know what this represents? Activation energy. Okay, so let's just start off with labeling. So here we have the activation energy. Good. And then here we have the reaction without a catalyst. So the energy required is high. You can tell, can't you? Because obviously a lot of activation energy is needed. Whereas with a catalyst, as I said, it provides an alternate pathway over here, and it and it lowers the activation energy. So it doesn't need as much energy to react, and it goes exactly down there. So do you understand how a catalyst operates, how a catalyst works in terms of the rate of reaction, how it would speed up the rate of reaction by lowering the activation energy for an exothermic reaction in this case? Good. So I just want to make it clear that this side is the reactants and this side is the products. And this basically means enthalpy change. Again, this was covered in a previous class course, so I won't go into detail with it. Okay, so again, let me just quickly write that this here is the activation energy with the catalyst used. Also, just say, if you don't understand anything, just please say no. Does anybody not understand this concept? So ask questions if you do not. No, I don't understand. Which part do you not understand? What aspect do you not understand? How do catalysts lower activation energy? So they lower the activation energy by providing an alternate pathway. Give me 1 second. I'm just going to reshare my screen. Just let me know when you can see the screen again. Is everybody able to see it? We can see it. Okay, perfect. Let me go back to the questions. Can you tell us what the sign means quickly? Yeah, so it basically means enthalpy change. Does anybody here actually know what enthalpy change is before I move on? Some examples don't require it. So if you've never heard of it before, then do not worry. So it's to do with bond energies. Again, this is, if you've never heard of it, do not worry, because I'm not too sure if AQ actually requires bond energies, but it's basically to calculate enthalpy change, it's the total energy absorbed to break the bonds minus the total energy released in making bonds. So yeah, it's in the A-level chemistry spec. Something that was definitely in the IGCSE spec, that was brought down from A-level to IGCSE. That's why I don't really want to get into it. We did do another crash course covering the whole of endothermic and exothermic reactions and bond energies. So if you are stuck on that, then you can. The energy change from reactants to products. Exactly, yeah. So it's basically the energy required, total energy absorbed to break the bonds from the reactants, and then the total energy released in making the bonds for the products, minus that, and you get the energy change or the enthalpy change. Okay, so it's just enthalpy change. Great. Okay, we now have endothermic. Question? Yeah, Anna, what's your question? Going back to the other graph, yeah. Why are the curves so different? Okay, so in terms of the curves, they represent how fast the reaction is happening. So here is the reaction without the catalyst. So it needs a lot of energy. It needs a lot of energy for the reaction to occur. Whereas with the catalyst, it requires little energy for the reaction to occur. And that's basically what it means. So with the catalyst, it would be a faster rate of reaction. Oh, I see. How would a typical exam style question look like on it? It'll basically be, it might be labeling. A lot of it, my exam board used to like to ask us to label these diagrams. For example, it would show us this and this arrow, and we'd have to say it's the activation energy. But I can go through that at the end if I have time, but I'm just conscious of time. Okay, let's quickly go into endothermic reactions. This is a bit more confusing. I didn't really like endothermic reactions because remember that the reactants are over here and the products are over here. Can someone quickly just tell me what an endothermic and exothermic reaction is, just so I know that you actually know what the difference between these two are, X and end. Exo, released, exit, good, yeah, good. Exothermic, endothermic reaction takes in energy from its surroundings. Good. Great. Okay. So here we have the reactants and here we have the products. Here we have our enthalpy change. Don't you worry too much about that. So here we have the activation energy. Here we have the reaction without a catalyst. And we can see that the activation energy with a catalyst is shorter. But without a catalyst, the activation energy is greater. Sorry, I didn't mean to say shorter, I meant to say lower. So again, it just shows that if you use a catalyst, it lowers the activation energy, meaning that the rate of reaction, so that the rate of reaction is increased. So does everybody understand that? Does that mean all reactions are reversible in theory? No, no, you can't. No, that wouldn't make sense. Examples are like, so someone asked for example, so for example, burning. Burning, what sort of reaction do you think burning is? Exothermic or endothermic? Fine, good, exo. What about like an ice pack? Like, you know those ice packs in first aid? Yeah, okay, great, because they require energy. Energy is taken in. Good, okay. Finally, reversible reactions. Can someone name a reversible reaction? Again, not too hard. This sign is a reversible reaction. That shows that it's a reaction, reversible reaction. Haber process, good. Again, I'm not going to go through Haber process just because there was another crash course on this. Reversible reaction. So a reversible reaction, it's basically, let me give you a simple one. Melting chocolate. Melting chocolate, can that turn back into like the solid chocolate? Good. Yeah. Can someone name me a irreversible reaction? Because they're like common. They're really common. Burning, cooking an egg. Yeah. So that proves that like changing, like that proves that not all reactions are reversible, because you can't uncook an egg, can you? Okay, so an example of a reversible reaction is the thermal decomposition of ammonium chloride. So thermal decomposition. Do you know what thermal decomposition is? Decomposition of ammonium chloride. I'm just breaking, yeah, thermal decomposition. Why am I, like, my spelling is so bad today. Decomposition, thermal decomposition of ammonium chloride. So thermal decomposition is basically the breaking down of a substance using heat. That's all it is. And it's a reversible reaction because basically ammonium chloride is a white solid. However, when it's heated up, it breaks down into two substances, the gas, which is ammonia, and it also breaks down into hydrogen chloride. And that's basically the forward reaction. Again, I won't talk about forward reactions and backwards reactions because that was done in the previous crash course. But if you let those two substances cool, what happens? They sort of reform the solid, which was ammonium chloride. and that's the backward reaction. So this, this arrow is the forward reaction, the top one, forward. This one is the backward reaction. Do you understand that? Just say yes if you understand it. Should this experiment be done in a closed system? Yes, it has to be done in a closed system. We come on to dynamic equilibrium in a sec. I don't get the sign. Basically, the sign represents a reversible reaction. So let's say X and Y are two substances, and so X and Y react, and they produce Z and C. Now Z and C can react again and produce X and Y. What is a closed system? So that's a good question. So nothing can escape. So our Earth is a closed system. Does anybody know why our Earth is a closed system? Because nothing can come in or go out. For example, water can't escape. It can't come into the Earth. So we have like, we can't have more sand or like more water. Like our water on the Earth is all, we're never basically going to run out of water. But that's not in terms of like drinking water is completely different, because that doesn't count. We can run out of drinking water. Earth as in ground or Earth, as in like the Earth. But that's why in geography, Earth is a closed system when learning about the water cycle. Okay, why do reversible reactions exist? I have no idea. I have no idea. Okay, so another reversible reaction. Has everyone heard of copper sulfate? This you should have done in primary school, not primary, secondary, year 7, year 8, year 6. The crystals, you like make crystals in your science lab, let them cool. They're like blue crystals, evaporation, that in like your crucibles, it's like a blue nice crystal. Basically, that's also a reversible reaction because remember when you heat up the blue copper sulfate, which is hydrated, which has water in it, it becomes dehydrated and it becomes white. But when you add water to that, it becomes hydrated and blue again. So that's why it's a reversible reaction. What is crystallization? Again, won't go into too much detail about crystallization. It's basically the process of, so you know how, I'll try being simple with this. So let's put sugar into boiling water. Sorry, sugar into water. We like boil the water and we're left with sugar crystals. That's crystallization in simple terms. Anhydrous and hydrous copper sulfate. Yes, those are the two types of copper sulfate when I'm talking about the reversible reaction. So the dehydration of copper sulfate is an example of a reversible reaction. Good. Okay, so let's quickly talk about dynamic equilibrium. If a reversible reaction occurs in a closed system, so for example, in a closed system where nothing can come in or go out, then it's something called a state of dynamic equilibrium, or equilibrium will be reached. Does anybody know what equilibrium is? This actually scared me because, yeah, I remember chemistry last year. Yeah, it basically means balanced. So basically the forward reaction and the backward reaction are the same, exactly. Just like Mariam said, the forward reaction, which is this one up top, the backward reaction occur at the same rate. Good. So basically it just means that the reactions are both taking place in both directions. So reactions occur in both directions. So just like Khadija said, so when the forward and backward reaction happen at the same rate, forward reaction, backward reaction go at same rate. The way I remember this was just like by diffusion, because I remember like the particles always reach equilibrium. They always like diffuse and they don't like accumulate on one side. Yeah, so it's basically another name. No. Dynamic equilibrium is not another name for a reversible reaction. A reversible reaction, if a reversible reaction occurs in a closed system, the reversible reaction will reach a state of dynamic equilibrium. So they're not the same thing. Or you can say, depending on your exam board, you'll have to either say dynamic or equilibrium. Yeah, dynamic equilibrium or equilibrium. What else do you have to say? What do you have to say about the effect? Does anybody know what you have to say about the effect? Why is paper 1 for chemistry even a thing? Paper 2 is so much better. Like who cares about ionic covalent? Oh my God, I understand. I honestly prefer organic chemistry. Organic chemistry is so fun. It's like so easy to get your head around if you get it. I was struggling with it at the beginning. But oh, I hated it. This is paper 2. It depends what example you're doing. For me, this is paper 2. System count. Yeah, so good. So basically the effect is nil. But what do I mean by that? Does anybody know what is meant by the effect is nil? There isn't one. Yeah. So basically the forward reaction. Oh, my thing stopped sharing. Let me know when you can see it again. Basically the forward reaction and the backward reaction cancel each other out. Forward reaction and backward reaction cancel. So does everybody understand what I mean by that in terms of cancel out, if two equations cancel each other out? Good. Basically, the reactions are taking place at exactly the same rate in both directions. Great. Okay, so we finished dynamic equilibrium. And now we have to go on to the bad bit, which is changing temperature and pressure. Again, this is basically just a quick recap from the previous crash course. Changing temperature / pressure. What can that do? Get more product. So if you change the temperature or pressure, you can gain more product. So remember, in a reversible reaction, the position of equilibrium depends heavily on the temperature and the pressure of both of the mixtures or the reacting mixtures. So if you change the temperature and pressure, you can basically move the position of equilibrium, so that gives you more product, or you can like change it so it gives you less product or less reactant, and so on. So for example, to get more products and less reactants, what would you do? What would you do in terms of, so like, what do you think you'd do if you want to get more product and less reactions? Good, yeah, so you'd move the position of equilibrium. So the position will shift to the right. Good, okay, so let me quickly write this down for you because it is a bit tricky. Again, I'm not too sure. Depends on your exam board if you actually need to know this. If you're doing edX or GCSE, you definitely need to know this. So so basically, you know that in terms of exothermic reactions, every single reaction is exothermic in one way and endothermic in the other way. So if you raise the temperature, the endothermic reaction will increase So, and that will use up extra heat. Does everybody understand that? Because if you raise the temperature, the endothermic reaction will increase because it uses up more heat, because it takes in heat. So remember, there's an endothermic reaction and an exothermic reaction in the reaction. Good. Whereas if you reduce the heat, if you reduce the temperature, the exothermic reaction will increase, and that will give out more heat. It's really, really, it's really confusing. But do say yes if you do understand this. Say no if you don't understand this. Yes, yes, yes. A few people are no. Okay, so a few points we need to note. So all reactions are exothermic in one direction, and endothermic in the other. So remember when I talked about backward and forward reactions over here, where is it? Over here. One of these is endothermic, one of these is exothermic. Does everybody get that so far? Now, remember how I told you about exothermic reactions and endothermic reactions? One uses heat, one gives out heat. So if you raise the temperature, what do you think that will favor? Do you think that will favor the endo or exo? And why? Why do you think it will favor the endo? Everybody's saying endo. Endo, good, exactly. It needs heat. Now, what if you lower the temperature? What if you lower the temperature? It stopped showing again. Give me a second. What happens if you lower the temperature? Does anybody know? What would it favor? Yeah, so raising temperature favors endo, and lowering temperature favors exo. Does everybody understand this so far? So I've done this a bit slower. Just say yes if you do understand this. Exo as it releases energy. Good. Great. So that's basically it. So if we raise the temperature, the endothermic reaction will be favored. So it uses up the extra heat. Whereas if you reduce the temperature, if you lower the temperature, it favors the exothermic reaction. So the exothermic reaction will increase and it will give out more heat. So do you understand that? Good. Now, what about adding a catalyst? What happens if I add a catalyst? What effect will that have on the position of equilibrium? Speed it up, no effect. Increase endothermic. No. So the person that said no effect, Ada, you are right. So the catalyst has no effect on the position of equilibrium. Does anybody know why though? Why might a catalyst not have any effect on the position of equilibrium? Yeah, it's not used. No, I don't think that would get you any marks. No, it's basically because it favors, it speeds up the both forward reaction and the backward reaction at the same amount. It doesn't favor one of them or the other. It basically speeds it up at the same amount. So do you get that? So a catalyst, say yes if you understand, has no effect on the position of equilibrium because it favors both forward / backward reaction. Great. So does everybody understand that in terms of temperature? Say yes. Is that better? Pressure is a little bit different, and I hated this. Pressure. I really do feel your pain because chemistry was literally the worst GCSE ever. You wrote it has no effect. Sorry, didn't. Great, thank you so much for spotting that. Catalyst has no effect on the position of equilibrium. Okay, let's quickly talk about pressure. So what do you think happens if we raise the pressure? It increases favors the side with the least molecules. Good, yes. And if you lower the pressure, it favors the reaction which produces more molecules or more moles of gas. So I'm going to quickly explain this. So remember that most gaseous reactions have more moles of one gas on one side than another. So most gas reactions have they have more moles of gas on one side, have more moles of gas than on the other. So good. If you raise the pressure, it will encourage the reaction which produces fewer moles of gas. Does everybody get this? It encourages the reaction which produces the fewer molecules, fewer moles of gas. But if you lower it, it will encourage the reaction which produces more moles of gas. Favors sides with less molecules. Yeah, good. Why? Does anybody know why? What's a mole? Again, so moles, the calculation for a mole, we're going to do a crash course soon. It should be on the website, but moles, have you ever heard of the Avogadro constant? Does anybody know what a mole actually is? Not the animal. Say, can someone tell me? Or does anybody know what Avogadro's constant? MR divided by mass. Yeah, it's, I don't want the formula. I want, like, does anybody know what a mole is? One molecule of a substance, like the total mass of something. Oxygen 16, that's the MR. 1 mole. Yeah, good. Avogadro to the power of 23 is Avogadro's constant. I don't know that. I don't know Avogadro's constant. I don't know Avogadro's number off by heart. It's a unit. Yeah, good. So if you raise pressure, do you know what raising pressure means? You increase the amount of molecules per in the specific area. So let's say this is low pressure. This is a higher pressure, because it compacts the molecules. So if you raise the pressure, it will encourage the reaction which produces fewer moles of gas. But if you lower it, if you lower the pressure, it will encourage the reaction which produces more moles of gas. So looking at a past paper question, in terms of, can you just tell me, can you put in the chat if you're doing triple or combined? So normally in exam questions, you'd probably get asked to define a reversible reaction, explain the term reversible reaction, and you'll also be asked you'll be asked the question, what is dynamic equilibrium? So what is dynamic equilibrium is usually a 3 marker, and a reversible reaction is a 1 marker. So to answer what is a reversible reaction, does anybody know? A reversible reaction is where the products of the reaction can someone finish off? Where the products of the reaction can be reversed. To turn back in, yeah. So the products of reactions can react with each other and convert back to the original reactants. Can you use freezing water as an example? Probably, I don't know. I'd probably stick with the ammonium chloride or copper sulfate. Yeah, stick with ammonium chloride and copper sulfate. Now, what about dynamic equilibrium? Explain what is meant by dynamic equilibrium. Can somebody explain it? It's a 3 or 4 mark question, depending on your exam board. In a closed system where backward and forward reactions are equal, that won't get you all 3 marks. No one has gotten all 3 marks yet. Rate of forward reaction is no one has gotten all 3 marks yet. Give me a proper, give me a full answer to the 3 mark question. So let me quickly tell you. So the dynamic equilibrium within a closed system. So 1 mark. So in the mark scheme, it will say closed system as 1 mark. The next point is that the reactions are taking place in both directions. So both directions will be another point on the mark scheme. The third point is the effect is nil. Good. The fourth or extra point is that both forward and reverse reactions cancel. So the cancel will be a keyword on the mark scheme. Cancel each other out. And they will take place at exactly the same rate. Can you write it down? Yes. So dynamic equilibrium. I think I wrote it down up here. So I'll add to that. Yeah, so it's basically here. So to get your marks, you'd have to say, so on the mark scheme, it's basically say both directions, forward plus back, same rate, nil, forward reaction, back, cancel each other out. Is there anything that I've missed? I've missed closed system. So remember, dynamic equilibrium is only really reached in a closed system. Nil basically means nothing, sorry. So there's no effect. Nil effect. And just remember that a closed system, that might suggest, like explain what is meant by closed system. It's basically when none of the reactants or product can escape, nothing can come in and out. So does everybody understand that? Everybody will be getting all of these notes. Do not worry. They will all be sent to you. What advice about doing revision would you give to those who have GCSEs this year? Stay consistent and do past papers, because your exam board topics have been released. So do past papers. Do you get the feeling that you haven't revised enough? Oh, yes, I have. I always feel like this. It's scary. I feel like I haven't revised enough, but I don't know. At the moment, I don't know. I've got my exams in 20 days. So the thing is, if I'm being honest, I don't know how I deal with it. I don't know how I did deal with it, because it was just like, it's like GCSEs feel like a blur. Will these topics be in year 9 papers? Again, it depends on your school, what your school have taught you. What A levels are you doing? I'm doing English, Latin, and French. So no sciences, but sciences were so good. I loved them, but then I could never imagine myself doing A level, apart from bio, which I loved. Okay, so has this crash course been useful to everybody here? Just say, it would be great if you guys could rate this lesson out of 10. Where can you find other crash courses? So other crash courses should be available on revision.com. Give me a second. So in terms of the ones that are upcoming, they should just be on the same page as you found this one. In terms of previous crash courses, if you go to the store, they should all appear there if it loads. Are there any maths crash courses? I do not know, actually. I think there is one. I don't think Wi-Fi will let me do it, which is annoying. But yeah, basically they're all on the store if you want previous crash courses. They'll come with the notes, the recording, and everything. But hopefully this has helped you a lot. But yeah, thank you everybody for joining. It would be great to see you in another crash course this week. And it seems like it is loading slowly. So if anybody does want to wait and see where the crash courses are, then feel free to stay. Is your iPad in French? It is in French, yeah. What are you doing this when does your holiday start today? No, it's not going to work. Okay, thank you guys so much for joining. If you have any questions, feel free to DM me on Instagram. My Instagram is revision_. But yeah, it was great teaching everyone. See you in the next crash course. Bye, guys. Bye.